So let's continue our exploration of the bivariate probability functions with a discussion of the bivariate distribution function. So we've talked already about the PFs and the PDFs for the bivariate case. So this is a situation where you have two random variables that are being determined simultaneously. So now we're going to see how you can get to accumulate these probabilities from these functions through the means of the distribution function. So we have seen this in the univariate case, so this is simply an expansion to the bivariate case. So the definition here, for any two random variables, x, y, we can define a function, capital F. Remember, always for the distribution functions, we use capital letters. That is defined in the domain of R2, right? Obviously, because you have two random variables. So if you had three random variables, this would be R3, and so on and so forth, right? And that function is essentially a mapping from this space to the space of 0 and 1, inclusive of 0 and 1. Why is that? Because we are essentially taking values of x and y and we are translating them to a probability, right? That ranges from 0 to 1 to 0 to 100% if you want to think about it this way. So such that that function, capital F of x, y, remember two arguments in the bivariate case, is going to be giving us the probability that x, the random variable x, takes a value of less or equal than this specific x value, the lowercase x, and your y random variable takes a value of less or equal to lowercase y. So think about these two things as being specific numbers here. Okay, and that holds for any x, y in the space of real numbers. So the function capital F is then going to be called a bivariate distribution function. This is the important part, to identify this function as a distribution function. So for those that have already solidified the concept of a distribution function, this is simply an expansion along the dimension of yet another random variable that is jointly distributed with x. So the structure of this presentation follows our standard approach. You have a case of the discrete distributions and the case of the continuous distributions. So if x and y have a joint discrete distribution, then you are going to calculate effectively this cumulative distribution function, the CDF, as the sum or the double sum of your PMF, right? The probability mass function for this bivariate case. How do you do that? Well, you define sort of your probability mass function. Notice here that, again, I am playing around with the notation because I want x and y to be introduced into this expression as you are summing things up to a specific value x or a specific value y, and sort of appear in your distribution function, right? So essentially, as this summation operation gets conducted, effectively this t variable gets substituted by this x parameter over here, right? And you don't have to define this as a number, you can leave it simply as x. So once you sum over y or over s, again, this y parameter is going to show up in the cumulative distribution function. So this is the case for the discrete random variables. How about the continuous random variables? It's very similar. Instead of summation signs, this time you're going to be using integrals. How do you define those integrals? From infinity up to a value of y, from minus infinity up to the value of x, of your PDF in this case of the continuous case. And notice again I have adjusted the arguments inside this PDF, the lower case f, to reflect a variable that is going to be matched up with y. So once you make the calculation for this integral, x naturally becomes part of the functional form here. Schematically, it's also important to think about a bivariate cumulative distribution function. Essentially, what you're defining is the sort of probability of falling within a space up to a particular value of x up to a particular value of y. So this is the footprint effectively of this cumulative distribution function that defines sort of this space of x and y for which you're going to be calculating the capital F. An example here involves giving you a PDF. Let's say this one that we have seen before. Remember that this is an example that we have worked through. We know that 1 over 96 times y is a PDF for these particular ranges of x and y, and 0 otherwise. The question here is find the cumulative distribution function that corresponds to this particular PDF. Well, what would you be doing? You would be going back to the definition of a continuous cumulative distribution function. Let's say the one that you have over here, the one that I just showed you. You would be effectively substituting this functional form inside here. You would be also utilizing the symbols, right? And then you would be calculating the double integral from theoretically minus infinity up to y for this functional form. Notice that in our case over here, x is bounded at 0 at the lower level, so that would be 0. Y is bounded by 1, so that would not be minus infinity, that would be 1, and everything else would sort of fall into place in sort of the standard way of thinking about solving this double integral problem. So give it a try, and you will see the solution in the next few minutes, actually, indirectly though, not directly. You still have to do the double integration. So let's move on to another topic that relates to these cumulative distribution functions. The question of how you can determine a joint PDF function if you're given a joint distribution function. So essentially the reverse of the problem above. If you have this capital f of x comma y, how can you identify this lowercase f of x comma y? So the idea here is that if you have x and y random variables that have a continuous joint distribution function, capital F of x comma y, then you can identify the joint PDF as the second derivative of this f function, right, del 2 of f over dx dy. That's sort of the standard definition of the second partial derivative, and we're talking about the cross partials over here. An example for this one. Let's say that I'm going to give you a capital F of x comma y, the joint distribution function, as 1 over 384 squared times y squared minus x squared. And I'm going to say that this works as a distribution function for x that ranges between 0 and 4 and y that ranges between 1 and 5. You should be suspicious already because these are effectively the intervals for which this PDF is defined. So maybe these two functions are somehow related. Let's see how this is going to work out. So the question is find lowercase f of x comma y for these spaces, these domains for x and y. How do you do this? Well, we simply are going to apply the definition over here. We're going to take the second derivative of this capital F function with respect to x and with respect to y. So this is the way to write this, del 2 del y of this functional form that I have already given you, this f of x comma y. Okay, this is the equivalent expression to this thing over here. Perfect. So once you do that, let's say first you can take the derivative with respect to y, given the way that we've specified the second partial over here. So del over del x, and let's say you do this derivative with respect to y first. So this 2 is going to come in front over here. So 2 over 384 x squared times y minus x squared. There's no y over here, so this is sort of the same thing as if it was a constant, so that's going to drop out. So you have this expression that then you need to take the partial derivative now with respect to x. So if you take the partial derivative with respect to x here, that 2 is going to come to the front, so 2x effectively and the rest stays the same. So 2 over 384 times y times 2x. You do this calculation, you get a 4 over 384 times x times y. Well, if you actually simplify this, you get to the expression that we had above, 1 over 96 times x times y. So we figured out that this expression over here is actually the distribution function for this particular joint PDF, which is it was sort of good to find out, and I think you all would agree that it's sort of an easy calculation to go from a distribution function to a joint PDF, because simply you're using derivatives rather than integration. From your knowledge of calculus, you should be aware that Young's theorem suggests that the cross partials are equal. So if I attempted to do this slightly differently, so for taking the derivative with respect to y first and then the derivative with respect to x, we would be getting exactly the same result. So in this space of bivariate distributions, PDFs, PFs, CDFs, we need to develop one additional concept that is going to help us move towards the idea of conditioning one variable on another variable or multiple other variables. And that concept is the concept of the marginal distribution. So I will jump straight ahead to this idea of a marginal distribution, and you'll see that eventually it's a rather straightforward concept. So we're going to let, as usual, x comma y be these random variables that have, let's say, continuous joint distribution function symbolized with capital F of x comma y, and the joint PDF symbolized by the lowercase f of x comma y. We are going to define a function f subscript 1, capital F subscript 1, as equal to, or essentially signifying the probability that your random variable takes a value of less or equal than a specific value x, being equal to the double integral of the joint PDF, where the difference here is we only constrain x in terms of the upper limit for the inner integral, and we do not constrain y at all. What is the meaning of this? Is that we're going to be agnostic about the value of y, right? So we are not going to try to define a probability where y is constrained by any value. So essentially we're going to let y take all possible values essentially in this summation exercise, and we're only going to be focusing on the behavior with respect to x. So essentially we're going to say, well, we are in this space of jointly distributed x and y variables, but we're trying to pick up only information that relates to x, right? We're not going to give any consideration to what is happening with y. So that's why we're going to let y range from -infinity to infinity for this integral. So how do you solve something like this? You might have to operate sort of the idea of limits. For those of you who are familiar with this particular construct from your days in calculus, essentially we are going to make the calculation as the limit of this double integral as y goes to infinity by sort of imposing an upper limit y over here, and then solving this with respect to the limit, which is fine. I think the most important thing to note here is sort of the concept of what is happening with respect to x, what is happening with respect to y in the definition. Equivalently, you can define another distribution function, capital F subscript 2 of y, that is going to be providing you with a numeric value of the probability that your random variable y takes a value of less or equal than y. This is the reverse problem to the one that we just saw, where we don't care in particular about specific values of x. X can be whatever, but then we're going to simply try to accumulate the probability that you're going to be sort of getting a value of y up to a particular point. So this is reflected here by this integral ranging from minus infinity to y, theoretically, while we let x range from minus infinity to plus infinity. We're not caring about the specific values of x. We're essentially summing out x from this calculation. Similarly, you can use the limits concept to arrive at a calculation for this distribution function. We're going to see what this is more practically as we move forward. So once you define those two functions, f subscript 1 of x, that's missing here, it's not necessarily needed because of the subscripting, and f subscript 2 of y, a function of only y, are called the marginal distribution functions of x and y respectively. So we can rewrite the above. We could do exactly the same thing. We just would be replacing integrals with some symbols, but the idea for the marginal distributions is the same across discrete and continuous concepts of random variables. So we can continue on the definitions of marginal distributions and move on to the sort of the equivalent of the joined PDF. You'll notice that in this particular case I started with the definition of the distribution function, a marginal distribution function, and now I'm going to move to the definition of the marginal PDF. It really doesn't matter. I think the concepts are there, and whether you're going to refer to one or the other one, first or second, doesn't matter. Whether you're only going to refer to a joined PDF or only going to refer to a joined distribution function doesn't also matter, because you can calculate one from the other. So then this is usually what you're going to see in the literature, that you're not going to be looking at both of these functions. One of them is going to be reported, and if there is a need to calculate the other one, then you have the tools to do that. So we're going to let lowercase f of x comma y be the joint PDF or the joint PF of x comma y, depending on the discrete or continuous version of this idea. And we're going to say that if the random pair x comma y are discrete, the marginal PD of x, that is lowercase f subscript 1 of x in the parentheses, is going to give you the probability that x takes a specific value of x, right? Because we're in the space of joint PDFs now, so this is essentially what a PDF is going to show you, or a PF in the discrete case. So how do you calculate this probability that x is going to take a specific value? Well, you're going to sum up the values of f of x comma y. But how are you going to do this summation? You're going to sum them up across all possible values of y. So we're going to see an example of how this actually happens. Similarly, the joint PF, in this case or the discrete case, of f subscript 2 of y is going to be giving you the probability that y now takes a specific value of y. How are you going to calculate that? You're going to be summing out all of the x's, right? You're not, because you don't care about which specific value of x you are seeing emerging in this PF. So you're going to be doing that on the basis of all of the values of f in the joint PF function. So the idea here is that you are eliminating one or the other random variable in order to pinpoint and focus your attention on one of the two random variables. Just because you are in the space or you're in a world where x and y is jointly distributed does not mean that you cannot calculate the probability that one of these variables takes a specific value, takes the value of x. You can do that. You just need to sum y out of the picture. It's not that, and similarly, you can calculate the probability that y is going to take a particular value. How do you do that? You need to ignore x, so you sum x out of these joint PFs. We're going to see an example here. So f subscript 1 and f subscript 2 are going to be the marginal PFs of x and y respectively. Okay. In the continuous case, you're going to define the marginal of x as the integral now of this f of x comma dy. Okay, this is the same idea as summing out y in the discrete case, but we're in the continuous case. Theoretically, y ranges from -infinity to infinity. If you take the integral with respect to y, you're going to be essentially integrating y out of this expression. And similarly for the case of the marginal of y, right, where you're going to be integrating x out of this functional form. We're going to simply call f subscript 1 and f subscript 2 as the marginal PDFs of x and y respectively. Note here that these marginal probability functions are probability functions that follow the standard rules of probability functions, or the standard properties. So we expect them to be non-negative, that's property 1, and we expect them to sum up to the value of 1. So the first one should be rather intuitive as a property. The second one, so essentially if you have the marginal PDF or the marginal PF with respect to x of x, and you sum now across the space of all possible values of x, you should be getting the value of 1. How do you do that? In terms of how do you actually prove that this is actually happening? Well, you're going to have the sum with respect to x. Let's plug in the definition of f subscript 1 in here. So that's going to be another sum of the joint PDF summing across y's. So simply, this is the double sum of x with respect to x and y of the joint distribution. By definition, this is equal to 1 if this is an actual PF. Let's look at the now familiar probability table that we can get from a joint PF or PMF, probability mass function. We've seen something similar before. And I'm going to add one column to the right that is going to operate as a column that is going to capture the values of the marginal PF and the marginal PF of x, and one row at the bottom that is going to capture the values of the marginal PF of y. So the inner probabilities are things that you have already seen. So these are the probability that you're going to observe the occurrence of 0 and 1 simultaneously, 1 over 42, for example. So the task here is that if you have this probability table, you have essentially all of these values of f of x comma y, right, for different combinations of x and y. You can calculate f1 of x and f subscript 2 of y. Those would be the marginal PF values. So how do you do that? You have to go back to the definition that I showed you before and look at what actually you need to do. In order to get the marginal of x, you need to sum up the joint distribution values across the values of y. So how do you move across the values of y? The y range is across rows over here, so you would be summing up across all possible values of y for a specific value of x. Let's say you pin x to a value of 0. Let's sum up all of the values across essentially values of y in order to get the marginal of x value. So you can see it visually, or you can follow the sort of the numerical example here. Let's say that we're going to calculate the marginal of x for a specific value of x. That would be 0. How would we do that? Well, we would be summing up across all possible values of y when x is equal to 0. So we would be summing up 0 plus 1 over 42 plus 2 over 42 plus 3 over 42. And this is what I am doing here with the resulting outcome of 6 over 42. And that will be the marginal PF value when x is equal to 0. You can repeat this analysis for x is equal to 1 and x is equal to 2 and fill in those two boxes with the marginal PF values. You have to note here is that because f subscript 1 of x, the marginal of x, is a probability function itself, these three cells need to be adding up to 1 based on the properties of PFs and PDFs. Similarly, you can do the same thing for y. So what would you be doing for the marginal of y, f subscript 2 of y? you would be summing up values of your joint distribution. Remember, the joint distribution values are this inner table over here, right? So you'd be summing those up with respect to x, right? Across x's, and how do they range across the column, right? This is a range of x's across the column. So you would be pinning down a particular value of y, let's say y is equal to 0, and adding up across the columns, across the possible values of x. So that would be 0 plus 2 over 42 plus 4 over 42. You should be getting that calculation here. That's also equal to 6 over 42. That's by chance. It doesn't mean that these numbers are going to be matching, but what you need to pay attention to is that when you do the same thing for y is equal to 1, right, and sum up these three values to get a number, these four cells over here need to be summing up to 1 based on the property of marginal PFs. So as an exercise, as you go along, looking at your notes, fill in this table and make sure that the marginal PFs are working in the way that we have described so far. So you may remember the table that I showed you from our textbook, the Goldberger textbook, table 1.1, that showed the joint frequency distribution of two variables from a particular random sample. The two variables were income of households and savings rates for these households, so the percentage of income that each of these households was saving for a particular set of years. And we said that this frequency table approximates the probability table that we get from sort of these bivariate discrete distributions, these PMFs that we have been working with. And I'm going to show you that table again in the book this time around and reveal that there was an additional line that perhaps you didn't pay attention to the last time you looked at this table, that suggested that if you add up values across the columns, right, where the y variable ranges, in this case the saving rates, you're going to get the equivalent of the marginal of income. Okay, so essentially this one says the probability that you're going to get an income category of 0.5, whatever that is, irrespective of the savings rate, is this 0.041. The same thing holds for different levels of income. So essentially this row is going to reveal the probability of particular levels of income if you really don't care about what savings rate materializes. So the main message here is that the empirical relationship is not deterministic. If it was, only one cell in each column would have a non-zero value. So effectively, if you look at this table, if this relationship was deterministic in the sense that there was a very standard relationship between y and x, so y would be a function of x, you would expect one sort of cell being filled out and having a positive value across this table so that you form some form of a relationship between x and y, and all of these other elements of the table would be effectively equal to 0. But you see that you have materialization of different pairs of x and y across the different categories, and sort of that kind of a table gives you a sense of the stochastic nature of the relationship between the two variables. Even though that actually exists, it does not mean that you have to be thinking about x and y simultaneously. Even in this bivariate case or in the multivariate case, you can isolate the information for x, the information for y, and using concepts like the marginal distribution sort of pinpoint the stochastic behavior of each of these variables. So having seen the example of the discrete random variables x and y, let's move on to an example of a continuous pair of x and y's, and I'm going to introduce a functional form, a joint PDF effectively, that we're going to be working with a lot, and you're going to see in a variety of examples moving forward. The distribution that I'm going to mention or utilize is called the roof distribution, and that's based on the three-dimensional shape that it has. The functional form of the joint PDF for this one is x plus y. It's a rather simple construct, and the domain of x for this function is going to be between 0 and 1, and the domain of y also between 0 and 1, and takes the value of 0 for all other possibilities for x and y. So, if you want to visualize this distribution, you can obviously use some software and plug in the functional form and see how it looks in 3 dimensions. But it's actually a plane that starts at point 0 in one corner and reaches the point 112 on the opposite end. Right? So a plane is a very sort of simple 3-dimensional object that you can either plot by hand or use some software to do that. Now, is it really a PDF? It looks a little bit strange, right? It's not like a normal distribution. It's not like an exponential examples of which we have seen before. It's very easy to verify whether it's a PDF. And it has to follow the 2 properties that we have already mentioned. The f, lowercase f, has to be non-negative, okay, everywhere, and we can verify pretty easily that for these ranges of x and y, this is truly going to be a non-negative function. And then the second property has to do with, well, if you sum up across all values of x and y, are you going to be arriving at the value of 1 for this effectively double integral? This is something that you can do. So this is the general sort of value that we're going to try to attain. What happens as you integrate across all possible values of x and y. So if you try to sum up across all x's and y's, well, in our particular specification, the domains are limited between 0 and 1. That's fine. Our functional form is simply x plus y dx. This is something that you can sort of solve through your understanding of integration techniques. So first you can solve this, or you can work through this with respect to y, right? Integrate across y. That is going to introduce a y here. That's going to be y squared divided by 2, evaluated between 1 and 0. So you work through that calculation, and you're going to get this. You're going to get an expression of x plus 1/2 dx. How can you do this integration? That's also pretty easy. X squared divided by 2 plus 1/2 times x, evaluated also for the domain of 0 to 1. That's going to give you 1/2 plus 1/2, and this is all zeros over here, so 1/2 plus 1/2 is equal to 1. So this is a parenthesis, right? So we just verified that the roof distribution is actually a PDF, and now we can move on. What is our goal? Let's see how we can identify or find the marginal PDFs, f subscript 1 of x and f subscript 2 of y. Well, how do you do that? You have to go back to the definition of the marginal of x and the marginal of y. Remember, the marginal of x is simply your joint PDF integrated across all values of y. Easy enough to do. We adjust our endpoints for the integral to reflect the domain of y, and we plug in the joint PDF over here, and we calculate this integral in a similar fashion that we did before. That also gets us to an expression of x plus 1/2, and that applies for the range of x's between 0 and 1. So this is simply the marginal of x in the continuous case. So we have another function that is a PDF itself. It has sort of the same properties and gives us information of what the density values are when we in some ways disregard y from this joint distribution. Or you can go ahead and plot this and see how it looks like. In some ways, you're getting a glimpse from the marginal, you're getting a glimpse of how the joint PDF looks like. It's similar to looking at a crosscut, sort of a 2-dimensional figure that reflects a 3-dimensional figure, which is the actual f of x comma y function. So we can continue on and do the same thing for the marginal PDF of y, f subscript 2 of y. Again, from the definition, going back to the definition is the first step in all of these processes. right? So what are you doing? In order to get the marginal of y, you need to integrate out x from the joined PDF. How do you do that? You adjust the intervals for the domain of x, you plug in the joined PDF, the roof distribution, which is x plus y dx. You can easily calculate the value of this integral evaluated at points 1 and 0 and get your answer, which is y plus 1/2 for the domain of y. And you can also plot this for y and have sort of that visual representation of the marginal distribution, a two-dimensional sort of figure that reflects some behavior from a three-dimensional joined PDF. Now, you can very easily imagine that once we move further from this space of two random variables, the bivariate case, to a case of three random variables, your f is going to have three arguments here, let's say x, y, and z. You're moving away from the capacity to visualize those functions. So that's why we're focusing a little bit on the bivariate case, because you can see some three-dimensional versions of joined PDFs, and obviously the two-dimensional versions of the marginal distributions. So generally, you cannot construct GDFs, PFs, the joint distribution functions from information that you have from the marginals alone. You have to have some other information that relates to measures of dependence or independence, but we'll come to those concepts further along in the semester.